The last speaker of this session, Professor Luiz Gustavo Farah, from the Universidade Federal de Minas Gerais, and the title of his talk is on well-posedness and wave operator for the KDV equation.
Thank you. So first of all, I want to thank the organizers, Felipe and Hermano, to the invitation to give this talk today. This is my, again, I participated in the other two events, so I'm very happy to be here today. And I will talk about well-posedness, and at the end of the talk, I will also talk about the construction of the wave operator for the generalized KDV equation. So the equation that we are going to consider today is this equation, the generalized KDV equation, which is this one here, and with nonlinearity u to the power k plus 1, and doesn't matter the sign that you put in front of the nonlinearity here. The local analysis and global analysis here that we're going to show today is the same. So this is essentially what we call the Falcons in case and the Falcons in case, I mean, for the nonlinear Schrödinger equation and also for this equation. So we consider the power greater than or equal than 4, and when the power is 4, this is a special case which we call the critical generalized KDV equation. I'll try to explain why the power 4 is special in some sense. So we are going to consider solutions in the classical sublab spaces. And we also know that for this solution we have a scaling, and which shows that if U is a solution, this scaling is also a solution. This scaling solution is also a solution of our equation. And if we compute the H1s, H dot S norm of these scaling function here, we found this. And what we expect on this case is that generally we expect that if this power here, this power of lambda is positive, then we have local well-posedness. This is not happening in all the cases, but at least we expect that this is true. And actually, this is a classical result which was proven in 1993 by Kenny Ponce and Vega. And they actually prove that we have the HS theory when we consider S greater than or equal than 1/2 minus 2 over k, which is exactly when this power here is positive, right? And they also prove in 1996, together with Benir and Svanstedt, that this result is sharp in some sense, that we cannot expect well-posedness if we consider S below this bound here, right? And what we're going to show today, what I want to show to you today, by the way, I forgot to mention that this is a joint work with Ademir Pastor, which is here, finally. And so what I'm going to show to you today is another proof for this result. I mean, a simple proof for this result. And the result by Kenny Ponce Vega is this one, when we have k bigger than 4, then sk like I showed you before. Then, in some sense, we have global solutions with small data, right? This is this data, this is smallest assumption that we need in this case. And actually, they prove that the solution is global if we consider the norm on this space here, right? And which is interesting here is that if we take k equal to 4 and put right here in this power zone, if we compute this for k equal to 4, we have that this norm is exactly this norm here, right? Because I forgot to mention why we call this when k is equal to 4 is critical, because if we take k equal to 4 and put this here, we compute this and you see that this is 0. So actually, a good name for this equation is L2 critical KDV equation, right? Well, I mean, the best sub-level index for this equation is H0, which is L2 for us, right? And what we have here, if you put k equal to 4 here, this is 0. This norm is the norm L5x, L10t, and this norm becomes this norm right here, okay? So which is, in some sense, difficult to prove this result is to estimate this norm right here. Because this norm, they have this derivative in t here, which is a little difficult to make the computations. We use the classical Fourier analysis on Littlewood pilot theory. And what I'm going to show to you is that I'll explain like what happens when the critical case, when we put k equal to 4, like I mentioned before, we have these two norms, only these two norms here. And we can actually prove the same result for global solutions with small data right here. And the main tool to prove this theorem in the critical case is this estimates here. We can estimate the linear propagator for the equation, and if you take the solution from the linear equation, we can make this estimate, the L5x, L10t of this, the linear solution, then this is bounded by the L2 norm of U0. This is the main estimate to prove the theorem for when the case k equal to 4, or I mean the critical case. And this is our theorem here, and we, in some sense, we obtained the same result like Kenny Possevega did in 1993, but we replaced the norm, the derivative in time norm, by this norm here. The norm L5k over 4 x L5k over 2t. And if we put, again, if we take k equal to 4 and put here, we obtain exactly this norm here. So this, in some sense, another generalization of the result. And this is interesting because to obtain the estimate for this norm here, it's very easy since we have the Strichard estimate and also Sobolev embedding. I will show how to prove this. And this is, I'll explain our main tools here. Like I said, this is the usual Strichard estimate for the KDV equation. If you take the solution of the linear equation and you take these derivatives, obeying this relation between these numbers here, we obtain that this norm is bounded by the L2 norm of the initial data. And this was proved also by Kenny Possevega in 1991. Actually, they proved much more general result for oscillatory integrals estimate, and we can use this result to obtain in the particular case for the KDV equation, right? And by corollary of this Strichard estimate, we can also obtain this estimate here, which is almost the same, but instead of consider the L2 norm in the right-hand side, we consider the L2 norm of the derivative sk of the U0, right? And this is just the Sobolev embedding here. We put this guy here, and we use Sobolev embedding to obtain this derivative in x here, and then we use the result, the previous result, the Strichard estimate, right? And which is good because with this estimate in hand, we can prove the estimate L5k over 4x, L5k over 2t, which is the norm that I replaced by these derivative in time norms. And this is just, to obtain this is just an interpolation between the previous estimate and this estimate that was also proved by Kenny Possevega in 1993. So with this estimate in hand, we can give another proof to the well-Posner's result, and I will try to explain this. But we can also obtain the estimate for the integral term of the integral equation, and this is very easy since we have the estimate for the linear part of the equation in hand, we can use this type of argument, t star argument, and you can pass this inequality to the integral part of the equation, right? And this is what I wrote here, which is very simple. And I want to give you the sketch of the proof for the result. So as usual, we need to consider, we'll use a contraction mapping principle in some subset of the continuous function of R to HSK. And we define this subset like using this norm here, which is exactly the norm that I mentioned to you before, that this one here, we replace the derivative in time by this norm here. So to perform the contraction mapping principle, we need to consider the integral operator, which is given in the case of the generalized KdV equation by this expression. And we need to find this A and K, this A, a suitable A, in order to this operator here is a contraction. So we can find a solution. So I will only give the details for this new norm, because the other norms we can do the same thing, and we can also use the argument that Kenny and Ponceveca used in their paper. And first of all, we use the linear estimates, and we can bound this term here by the initial data and by this derivative here for the nonlinear term, right, in our equation. And so to bound this term here, we use the classical fractional rule. Actually, we split this nonlinear term here, uk plus 1, in two other terms like this, uk and plus u to the power k plus u. And then using the fractional derivative rule, we have that it will appear two terms. And the first term when this derivative hits this term here, and also when this derivative hits this term here. That's why I put these two terms here. And the first term we can compute like this way, and as you can see, this is the norm that we consider in this case, the new norm that we replace. And also we obtain this other term here. And which is interesting that if we compute exactly which is P0 and Q0, and we use the fractional derivative rule again, we obtain that the term that appears here is also bounded by this one. And since this P1 is given by this will cancel with this, and this will cancel with this, and we obtain the estimate that we are looking for, that this nonlinear term is bounded by this term product with this term. And as you can see, this is the two terms that appears in the definition of our space. So this is bounded by A, if you consider a ball on this space. And just taking the initial data is small enough, we can choose this classical argument where this is also, this phi, this operator phi is a contraction on this space, and we can also obtain a solution. And this is in a standard way. Okay, so this is our sketch of the proof, and which is, and as an application of this result, I want to show you another result about the construction of wave operator. Okay, how to apply these new estimates to construct a wave operator to this equation. And first of all, I want to explain what is this problem, the construction of a wave operator. And it is very simple to understand. Like, first of all, we take a profile V on a suitable space, and we are looking for a global solution, UT, such that at the infinite, this solution of the nonlinear problem behaves like the solution of the linear problem with V as initial data. So this is, in some sense, inverse scattering, like we are looking for the problem that it is the inverse of the scattering, right? And which is interesting in this problem is that we don't need to care about the size of V, because usually in the scattering problem, we are looking for global solution for a given initial data, and we can only guarantee that the solution is global for initial data, which is small enough in some sense. And which is nice in this kind of problem that we don't need to care about the size of these initial data here, because this initial data is only for, it's the solution for the linear problem with this initial data here, okay? And we know that the solution for the linear problem exists for all initial data here. So, and there are several previous works on this problem. For the nonlinear Schrödinger equation, I've referred the paper from Janib and Velo in 2004. Actually, this paper is like a survey. They review several results about this problem for the nonlinear Schrödinger equation and other nonlinear Schrödinger models, and which several authors work on this kind of problems. And another result for the generalized KdV equation, given which was studied by Cott in 2006, and also for the Boussinesq equation, I have a paper about this problem with scattering for this equation too. And here we'll follow the ideas developed by Cott in 2006 to prove the following result. We have that for the generalized KdV equation, we can construct a wave operator like for all initial data V in HASK dot, which is a nice result. And for every initial data V on this space, we can find a global solution such that behaves like the linear solution, which is interesting. And this is, in some sense, this is an extension of the Cott result. And they prove a similar result like this, but considering the initial data on this space with weights, right? So we can remove the weights. We can just consider the whole space H as K dot. And he also proved that this limit is 0, but replacing this space here by H1. Okay, so we have that this behaves in a larger space. And I want to show you a sketch of the proof. So we follow the ideas introduced by Cott, and to find a solution of this problem, we need to find a fixed point for this operator here. Okay, defined for large times. And this is a proposition that it was observed by Cotty, that if we find a fixed point for this operator, then we know that this guy here is a solution of the nonlinear problem, right? This is very simple to prove. So we just need to look for a fixed point for this operator. And the good thing is that it's very natural to prove this, since we have the estimates for the local result, global result. Just using the estimates, like I mentioned before, we can find a solution using the contraction Maple principle again, and we can prove like this, a similar estimate like we did before. And which is interesting here is that if you take t to the infinity, if you send t to infinity, we know that this guy here goes to 0. Then this guy here goes to 0 as we expect. So this is very natural once you have that the proof of the local result. And so it remains to show the limit that I put in the statement of the theorem. And this is easy again, because we know that this guy here is actually W, and W, since W is the fixed point of the operator phi, we know that this norm is equal to this norm, and we apply again the the nonlinear estimates, like we did before, and we just know that this guy here goes to 0 since this guy goes to 0, and also this guy here goes to 0. Okay, which is very simple. And so actually, I didn't put in my slides, but we can also have another application for this result. We can give a simple characterization of scattering, talking about scattering, not about inverse scattering. We can give a nice characterization for scattering for the generalized KdV equation, and we can show that if we have a global solution with the H1 norm bounded, and if this norm that we put in the local result here, so this norm gives us this new norm that we introduce here. If we have that this norm is finite, if we start with a global solution, we already know that the solution is global, and the H1 norm of this solution is bounded for all t. And if we know that this norm here is bounded, then this implies scattering, which is a good characterization of scattering, right? So I think that I will end here. So thank you.
Some remarks or comments? No? So let's thank the speaker again. So after leaving, please, Felipe is going to give us some very important remarks. I think it's money for everybody.
No. Okay, so I have several announcements. The first one is concerning the photo group that will take in on Wednesday at 10 a.m. Usually we have the picture in the third floor. Okay. The second one is concerning the luncheon of Wednesday too. And we would like to, well, people that wants to participate of the churrasco on Wednesday, we are asking to register till tomorrow at noon, okay, to have an idea how many people will participate of that activity, okay? People that go into the hotel, there will be transportation at the Hotel Everest. Will be transportation at 8 p.m., okay? And finally, I want to make an advertisement. So last June, we went to Padova, and IMPA was chosen to hold the 15th HYPE conference. So we will have in 2 years from now, the HYPE 2014. Okay, so before going to the next activity that is going to be the show Bossa Nova, I'm going to show the presentation that we had in Italy last June. Okay, you have to begin everything.
International Conference on Hyperbolic Problems, HYP 2014, Rio de Janeiro. The National Institute for Pure and Applied Mathematics, IMPA, is proud to propose its candidacy to host the 15th International Conference on Hyperbolic Problems, Theory and Numerics from July 28th through August 1st, 2014. Located in one of the most pleasant neighborhoods of Rio de Janeiro, close to the famous beaches of Leblon and Ipanema, near the lagoon, another one of Rio's postcards, IMPA neighbors the gorgeous botanical garden. It is built on the skirts of the greatest urban forest in the world, the Tijuca forest. IMPA IMPA is unquestionably the main mathematical research center in Brazil and one of the most important in Latin America. Since its creation in 1952, 693 students obtained degrees of Master in Mathematics, among which 556 are Brazilians and 137 are from other nationalities. And regarding PhD degrees, a total of 360 students obtained the title, being 194 Brazilians and 166 of other nationalities. Currently, IMPA has 43 permanent faculty members and an average number of 250 visiting researchers per year. IMPA is well known for its expertise in organizing successful scientific meetings, ranging from small workshops to conferences for more than 500 people, such as the Brazilian Colloquium of Mathematics, that takes place every other year, and which latest edition has been attended by more than 600 participants. IMPA's facilities include 3 auditoriums with total capacity of 400 seats, 200 in one of them and 100 in each of the other 2. They are equipped with the most modern multimedia devices, allowing simultaneous broadcast of lectures to all of them. There are 8 lecture rooms, 4 with 80 seats each, 2 with 40 seats each, and 2 with 30 seats each, besides a pleasant reading room with 100 seats and a cafeteria for lunches or snacks. IMPA's library has worldwide recognition for having one of the greatest collections of mathematical books and journals in the world. There we find 80,000 volumes, 980 titles of periodicals, and 35,000 books. Besides the impressive number of high-quality scientific publications produced by its own researchers and more than 800 preprints posted in its preprint server since 2001, IMPA has also strongly impacted the development of mathematics in Brazil and Latin America through its own edited collections of textbooks addressed to graduate and most especially undergraduate students. We are looking forward to seeing you in Rio.
Okay, so I invite you to... Okay, so I invite you to pass to the auditorium 1 where we have the show. Okay, thank you.